The U.S. Department of Energy's Carbon Capture Simulation Initiative, or CCSI, is a program designed to accelerate the development, scale-up, and commercialization of carbon capture technologies. These technologies enable carbon dioxide to be captured from the flue gas of power generation applications, transported, and stored safely underground. Carbon capture and carbon storage technologies are critical for reducing global greenhouse gas emissions resulting from fossil fuels. The development and scale-up of new technologies in the energy sector traditionally takes up to 15 years to move from the laboratory to pre-deployment, and another 20 to 30 years for widespread industrial-scale deployment. But the call for innovative, cost-effective carbon capture technologies is urgent. So the U.S. Department of Energy launched CCSI, a partnership among national laboratories, academic institutions, and industry, to identify barriers and challenges that need to be addressed to accelerate the development and deployment of much-needed carbon capture technologies. The CCSI toolset is an integrated suite of computational tools and models designed to help identify promising concepts more quickly and then focus development efforts to move rapidly from the laboratory to pilot plant and demonstration scales. By using advanced modeling and simulation tools, the CCSI toolset reduces the time and costs required to move new, cost-effective carbon capture concepts to commercial scale more quickly. Let's take a closer look at how the toolset works. There are many different technologies for capturing carbon dioxide from flue gas. These technologies range from solvent-based systems to membranes to solid sorbents. Since resources permit only a limited number of potential materials and technologies to be pursued, we need to quickly identify the most promising concepts and focus our development efforts on those. To do so, we need to be able to rapidly understand how different concepts would work within a complete carbon capture system. The CCSI toolset helps with this by providing a framework to take initial laboratory data describing the behavior of a carbon capture material, such as a solid sorbent, and synthesize a process that has been optimized for its specific characteristics. The first step in the development process is to collect experimental data in the laboratory showing how the proposed material interacts with CO2 and other components of flue gas. This data, along with other physical property data, can then be taken to the Process Systems Engineering Lab, where we can then create a basic data model which represents the material's behavior. CCSI's Sorbent Fit tool helps develop basic data models for solid sorbent materials. The next step is to integrate the basic data models into more complex models, representing potential types of equipment that could use the material to capture CO2 from flue gas. In the case of solid sorbents, these could be fluidized beds. Now, we want to connect the potential equipment to create a complete process that can not only capture CO2, but also recover it as a separate stream. This stream of CO2 can then be compressed and sent via pipeline to a geologic storage site. To synthesize this complete process, we need to determine which potential types of equipment to use and how to connect them in a way that minimizes the costs associated with CO2 capture. This is a very complicated problem. One way to address it is to use an optimization approach that embeds many potential options and uses a computer algorithm to determine the best configuration. CCSI developed the Focus tool, a framework for optimization, quantification of uncertainty, and surrogates to enable such optimization. The Alamo module in Focus creates simple algebraic models from the detailed equipment models to select the best set of equipment and determine its configuration. Focus can run hundreds of simulations in parallel in the cloud or on dedicated computing clusters to support this large-scale optimization, getting better solutions in a fraction of the time of conventional approaches. The optimized carbon capture process from Focus can be compared with other concepts, and the best option can then be moved forward for more detailed simulation and experimental development. The process design from Focus also identifies the likely equipment sizes and operating conditions that will be required. This information is the basis for even more detailed, three-dimensional computational fluid dynamics models of specific equipment that can be developed in a device-scale computational lab. Device-scale CFD models enable a thorough understanding of the internal behavior of equipment, which can reduce the time for troubleshooting new equipment. Device-scale models can also be rigorously validated at laboratory and pilot scale to provide quantitative predictions of how equipment will perform as it is scaled up. These detailed equipment models can then be used to improve process models, which could result in further improvements to the initial design. Throughout the development process, the CCSI toolset shares information and insights among physical systems device scale models, and process models. This capability helps researchers collect the right data and maximize the knowledge gained from physical experiments, pilot plants, and demonstration projects. By combining the advanced models and computational tools of CCSI with laboratory and pilot-scale experiments, technology developers can reach full scale faster, with lower risk and greater understanding of their process. Thus, industry using the CCSI toolset could decrease the time between laboratory research and deployment of new technologies by 5 to 10 years, helping to make advanced carbon capture technology available for commercial deployment faster. The CCSI toolset offers significant return on investment. Analysis shows that hundreds of millions of dollars could be saved by just one technology being scaled up faster and more efficiently. CCSI industry partners are already using the toolset, and CCSI researchers are improving the tools based on input from industry users. As the CCSI toolset reaches more users, the carbon capture technologies needed to curb climate change come closer to commercial deployment.